On to inverse functions. We will, but by the way, figure out how to differentiate exponential functions with other bases, like 2 to the x and 18 to the x and all those fun things, but not just yet. First, inverse functions. So first, a definition. F and g are inverse functions if the domain of one is the range of the other, and if f composed with g of x is the same as g composed with f of x, which just gives you x, the identity function. And this is for all x in the appropriate domain. And if this is true, then f equals g inverse and g equals f inverse. This is the notation for the inverse functions. It's a really awkward notation for us to use. Because for example, if we want to find a derivative of f inverse, we want to find like f inverse prime of x. It's just awkward having the inverse notation with the prime notation. Which is why a lot of times in questions, instead of using f inverse, you see the problem just say g is the inverse, and just use g instead. Just a lot cleaner to look at. And just one quick note on the definition of inverse functions. Pretty much what this means is if you plug g into f, they'll cancel out. And if you plug f into g, they'll cancel out. Right? So to write that a different way, this just means that if you plug the inverse into the function, hold on, I wrote that down wrong. If you plug the inverse into the function, it just gives you x, right? So the inverse and the function, they cancel out. Whatever the inverse did to x, f undoes, and you're left with just x. And the opposite's also true. If you were to plug f of x into the inverse, it just gives you x. Because whatever the function does to x, the inverse undoes, and you get just x. Actually, the best way to express the definition of the inverse is with this fact right here. Because all it does is just switch x and y. Like really, the inverse function just changes your input and your output. So it just switches x and y. So if the point a comma b is on the graph of f of x, then b comma a is on the graph of the inverse. Because all the inverse does is switch the x and the y. It takes the x and the y and it switches it around. This, by the way, leads to some cool and symmetric graphs. Like if, for example, we had some function that looked like this. I don't know, some kind of like cubic function. Well, since all the inverse does is switch the x and y variables, that makes the function and its inverse function symmetric about the line y equals x. So if that is the original function, the inverse function would just be the mirror image. It's actually pretty fun to go on Desmos, which is a nice, fun, free graphing website, and just graph functions and then just switch the x and the y and see what the inverse function looks like, because they have these cool symmetric graphs. And going back to this definition I gave you right there, if, say, like on the original graph, this point is what? We'll just guess like -4, 2. That means on the graph of f inverse, we're going to have 2, -4. Those are corresponding points. Those 2 points are the corresponding points on the inverse function. This is the result of the inverse switching the x and the y point right there.